Hi and welcome to this module on thermochemical conversion of biomass. In this module, we will introduce the most common thermochemical processes used to treat biomass. These are pyrolysis, gasification, and combustion. These technologies can be technically complex and expensive. However, we will focus only on cases and examples that are existing in developing countries. So, what is a thermochemical conversion? Thermochemical conversion implies exposing biomass to high temperatures, between 200 and 1500 degrees Celsius. These high temperatures, together with other parameters such as oxygen supply, use of catalysts, time, and pressure, decompose and depolymerize biomass into either intermediaries, which are used later to synthesize more complex products, or into its simplest constituents such as water and CO2. Let's briefly describe some basics of each technology. We will start with drying. Although drying is not a thermochemical process on its own, feedstocks need to be dried before being processed. This occurs at temperatures up to 100 degrees. Pyrolysis is not only an independent process, but the core reaction of all thermal processes. It is the first step in the gasification and combustion process. Pyrolysis occurs when biomass is thermally decomposed at temperatures between 300 and 600 in the absence of oxygen. The absence of oxygen can also be explained by lambda, which is the little figure that you see there. Lambda is the ratio between the oxygen supplied to the thermal process and the oxygen required stoichiometrically for complete combustion of all organic compounds. In this case, therefore, lambda is 0. Broadly speaking, two types of pyrolysis can be distinguished: slow pyrolysis and fast pyrolysis. These vary on several process conditions. Retention times, for instance, are around 1 second for fast pyrolysis and can last several days for slow pyrolysis. The process results into solids, namely char, liquids, called bio-oil, and a mixture of gases, some of which are fuel gases, also called pyrogas, and some of which are combustion gases, such as CO2 and water vapor. The relative proportion of the output materials depends on the process conditions. In slow pyrolysis, approximately 35% of the input is turned into char, 30% into bio-oil, and 35% into gases. Whereas fast pyrolysis obtains much more liquids, around 75% of the input, and lower solid and gases, 12 and 13% respectively. The reaction after reaching 280 degrees Celsius becomes exothermic and generates heat. Torrefaction is a form of mild pyrolysis which occurs at 290 degrees Celsius and lasts for 10 to 60 minutes. 80% of the input is turned into a solid product of higher homogeneity and increased energy density compared to the input material. The rest becomes gas. Let's move forward. Gasification is our next process on the list. This thermal conversion of organic material takes place at elevated temperatures, above 750 degrees Celsius, with a partial supply of oxygen, lambda ranging between 0.2 and 0.5. Retention times are short, ranging between seconds and minutes. In this process, 85% of the input material is then converted into a mixture of permanent gases: carbon monoxide, carbon dioxide, methane, and hydrogen, also called syngas or producer gas. Char would represent only 10% of the output, whereas liquids would only be 5%, consisting mainly of water and condensables as minor products. Combustion is our last process. Combustion occurs at higher temperatures, over 700 degrees Celsius, in the presence of oxygen, being lambda higher than 1. Burning is how you and me would normally refer to this process. Combustion is the oldest way of using biomass and accounts for over 97% of the world's bioenergy production. During combustion, organic matter is decomposed to produce mainly gases, carbon dioxide and water vapor, as well as ashes. The chemical energy is released as heat. In the ternary diagram, we can see how thermochemical processes shift materials in different directions based on their relative content of carbon, hydrogen, and oxygen. We see where biomass is located here in the middle. Slow pyrolysis, for instance, increases the relative carbon content, shifting the biomass towards the black area, char, a solid product. On the other hand, oxidation or combustion mainly yield gaseous products, such as CO2 and water, which can also be seen here in the diagram. Time for some clarification. We saw that char is one of the output products of these processes. But char, charcoal, biochar, did you ever hear these terms? Do you actually know what they mean? Let's see what are their differences. The term char is generally used for the solid product obtained from the thermal decomposition of any biomass, which has a high heating value of approximately 25 to 28 megajoules per kilogram. When char is obtained from less bulky biomass, such as leaves, small branches, plant seeds, coconut shells, etc., the final output might be too dusty to be burned directly, as the one seen in the movie. And therefore it requires briquetting. Briquettes have a lower calorific value due to binding materials used. When the biomass is wood, the material obtained through the same process is called charcoal. Charcoal is mainly used as fuel for cooking or industrial processes, as it has a high heating value of 31 to 33 megajoules per kilogram, much higher than the others. Most of the times, charcoal does not require any post-processing. Char can also be used as soil amendment, in which case is called biochar. This is the core idea of the Terra Preta movement. So, what products can we obtain from these thermochemical processes? We've seen that the primary products are char, bio-oil, fuel gas, and heat. From char, we talked about three market products that we can obtain: charcoal, briquettes, and biochar. Chars can also be refined into biofuel or other chemicals. Bio-oil and fuel gases can be upgraded through refinery in order to synthesize other chemical compounds or to be used as biofuels. They could also be consumed in turbines, engines, or boilers and produce electricity and heat. The heat obtained from combustion can be used in boilers to obtain electricity or directly commercialized. Thermochemical conversions are therefore promising considering the growing challenge of waste disposal and dwelling fossil fuels. Being aware that biomass represents the biggest waste fraction in developing countries, these processes might represent opportunities to valorize it. How are these processes currently being used to treat waste in developing countries? From the ones explained before, we will mainly focus on two: slow pyrolysis and combustion, since they are the ones that are being used. Let's have a closer look to them. Did you know that carbonization or char making is a slow pyrolysis process? We humans have produced char since the dawn of civilization. In developing countries, this is still a very extended practice, as it consists the main source for cooking fuel. 80 to 90% of urban households in sub-Saharan Africa, for instance, use charcoal for cooking and heating. Charcoal production in Africa was 29 million tons in 2011. This table here shows some big charcoal producers in the world. Although urban biowaste represents a potential feedstock for char production, the majority of the charcoal is derived from wood, which substantially contributes to deforestation. Let's have a closer look to the charring process. This figure here illustrates the changes in weight, volume, and heating value after slow pyrolysis of wood to charcoal. We see that the weight is reduced to 20%, the volume to 50%, and the heating value is doubled. During carbonization, materials are dehydrated and deoxygenated, resulting in a decrease of the hydrogen-carbon ratio and oxygen-carbon ratio. The Van Crevelen diagram is used to depict this. On the horizontal axis, we see the oxygen-to-carbon ratio, and on the vertical axis, the hydrogen-carbon ratio. These areas show where biomass and other solid fuels are located according to these ratios. Carbonization will shift the values of the original biomass in this direction. The length of the arrow between input and output ratios indicates the intensity of the process. The bigger the intensity, the more oxygen and hydrogen that are lost, lowering the ratios, and the better fuel properties that the output material has. This graph shows the impact of temperature on the solid yield. The lower the temperature, the higher the solid yield, which is partly due to a higher volatile matter content. With higher temperatures, more volatile matter is degraded, reducing the solid yield, but obtaining a cleaner and preferable fuel. High content of volatile matter in char, over 40%, is undesirable. Volatile matter facilitates ignition, but produces noxious fumes when burnt. The input requirements depend on the final use of the product, either if it's for domestic use or industrial use. In any case, having a moisture content lower than 10% is a requirement, which means that fresh biomass often needs to be dried beforehand. Feedstocks with high fixed carbon content are preferred, as fixed carbon provides an approximation of the possible char yield that we are going to get, while feedstocks with high ash content, like rice husks for example, or contaminated with inert materials such as sand, produce char with very high ash content, and this lowers the heating value of the char. How do we know when the reaction is finished? Look at the smoke. In traditional charcoal making, 3 stages can be characterized based on the color of the smoke emitted: drying, white smoke; pyrolysis, yellow smoke; and process completion of char combustion, blue smoke. Pyrolysis technologies can look very fancy, but actually, the vast majority of the reactors in developing countries are simple and functional. In this video, we see how cardboard is carbonized in a drum. The drum is closed after igniting the material. Part of the material will be combusted to provide the heat required to pyrolyze the rest. At the end, we can appreciate the volume reduction and the carbonized cardboard at the bottom of the drum. Okay, so we finished with pyrolysis. Let's say now a couple of words about combustion. Combustion is a waste management method spread out all around the world. Incineration plants, for example, combust the waste in order to reduce its volume and obtain energy from it. However, open burning of waste is a very common practice, especially in low and middle income countries. Open burning is any open flame exposed to the environment, where pollutants produced from the fire are emitted directly into the surrounding air. Many people in developing countries have burned trash for generations. People often burn because there is no other way to get rid of their trash. In this module, we learned the 3 main thermochemical processes, which are pyrolysis, gasification, and combustion. We also had a closer look, especially on slow pyrolysis, but also a bit on open burning, as 2 common waste-related practices in developing countries. For those interested in getting more insights about carbonization in low and middle income countries, we recommend this report, which is available for free on the internet.